4.3 half turn. Yeah, so in 4.2, we should have said the rotations with the same center form a group, yeah?
Yeah.
And the other thing was like the ones generated by ones of differing centers form a group, yeah? But to actually show that the ones with different centers form a group, you have to show that rotations composed of rotations about different centers give you another rotation. Okay? Otherwise you're outside of the set. Yeah? Okay. So half turn. One kind of rotation, that's a special kind of rotation, shares with translation the properties of transforming every line into a parallel line. This is a half turn through 180 degrees. It transforms each ray into an oppositely directed ray. Yeah? So if you think about complex numbers, rotating by I is 90 degrees, right? So if you times it by I squared, you get 180 degrees. Yeah? And I squared is just minus 1, right? So rotation should be xy goes to minus xy, yeah? Okay. Clearly, a half turn is completely determined by its center. Since a translation transforms each ray into a parallel ray, the effect of two half turns applied successfully is the same as the effect of a translation. That seems like it's the same as doing nothing, isn't it?
Oh no, you can choose two different centers.
Oh, you mean you have two different centers half turns?
Yeah, you pick
okay.
one center.
So if you have two different center half turns, it's the same as a translation.
Yeah.
Okay. Is that obvious, or should we have to investigate?
So we know that we point the right way, and we move around will stay the same. So yeah.
Ah, that's good. Yeah. So everything. Wait, a center of the heart. Yeah. So this is about the origin, I guess. Yeah. So that's important. Otherwise, it's not just that formula. Yeah. So that's a rotation at the origin. Okay, yeah, that's a good check. Okay, so obviously, if you rotate about this point, like, it'll make this into that, right? What does it do to something else? It turns. Yeah. Okay. So like it takes like this point here, right? There's another color. It takes this point here into this point here. Yeah. Oh well, it's on the same line now. Yeah.
And those don't have to be on the same line.
No, this is the rotating part.
Oh yeah.
Okay. And everything from this is like generic, yeah. And then if we rotate about another center, like here, yeah, then that point now goes to here, yeah. So we're saying, is this the overall translation? Yeah. Is it related to the original centers?
It should be double the distance in the same direction.
Double the distance of what?
the two centers. Like first
Oh, so there's like a center distance.
yeah, and that'll be double to this thing.
So this is 2D, you're saying?
Yeah, in the same direction. Well, that's true.
Wait, you're saying it's parallel to the distance to the center?
Yeah. I mean, it's obviously true with 90 degrees.
Okay, so let's have a look. So this is D, yeah? So this is convenient. Yeah?
Mm-hmm. And the two, yeah, it's only triangle. You see. Oh, actually, do you know this?
Okay, so hold on, let's just get back a step here. So
Yeah, because that side and that side.
we don't know the 90 degrees.
Yeah, but
Yeah.
you don't need that because the two rays are equal, right?
Which two rays? This, yeah?
So
this is the midpoint, yeah?
And the angle.
That means they're parallel, yeah?
Mm-hmm. You also know it's double because the rays.
Yes. Good.
Yeah.
Right?
Mm-hmm.
So this actually comes up a lot, this kind of setup, yeah?
Yeah.
It's converse and it has come up a lot. Alright, so it's a translation. Transforms each ray into a parallel ray. The effect of two half-turns applied successfully is the same effect as a translation. In brief, the sum of two half-turns is a translation. So the composition of a rotation with a rotation might not be a rotation. Yeah? Because a translation is not a rotation. Yeah? Translation has no fixed points, right?
Yeah.
Rotation has at least one. Okay. Okay, they didn't say that, but yeah, we were wondering about that before, so we got to answer our own questions, yeah?
Yeah.
So which reduces to the identity if the half turns have the same center, obviously. More precisely, if A, B, and C are evenly spaced along a line. Okay, what does this mean? A, B, and C are evenly spaced along a line. Is that what they mean? So that B is the midpoint of AC, the half turn about A leaves A invariant, and the half turn about B takes A into C. Well, yes. Thus, the sum of these two half turns is a translation through AC. That's what we said, right? It's a double in the same direction, yeah? Okay. It's good, we figured that out ourselves. Okay, so figure illustrates something about... Figure 4.3a illustrates the sum of half turns about O1 and O2. Shall we draw it? Let's draw it. Oh. I feel like I used to be able to constantly longer. Some kind of... Okay, so you got AB up the top, yeah? And then you got this... A double prime, B double prime. Yeah. I feel like we've kind of done this already, yeah? And then you have A prime, B prime. Okay, hold on. So you have this here, right? O1 gives you A prime, yeah? O2, it also gives you B prime. Yeah. O2 is... Oh, so A double prime is a reflection of O... about O2 of A prime, yeah? There gives you there, yeah? So you get B prime to B double prime through O2, and you go from B to B prime through O1, yeah?
And A double prime and A prime. No, we're missing a line. This is really
Alright, there you go. That's like a nosebleed for you. Okay, and we get a parallelogram. Yeah. Okay. The line segment is transformed first into A prime B prime, and then into A double prime B double prime. Thus, the sum of is a translation A double prime, yeah, or B double prime. Yeah. So is it obvious it's parallel? Yeah. So O1 prime, O1 O2 we said was parallel to something, yeah. So it's parallel to basically any other triangle that it's on.
Yeah.
So it's parallel to A double prime, yeah? Because that's the midpoints. And it's also parallel to B double prime, yeah? So they're parallel to each other. Okay? And the same reasoning shows AB is parallel to A double prime, B double prime. AB is on this similar triangle with A prime, B prime, yeah? Which is on another triangle with there, yeah? So it's parallel. Okay. Many old and familiar theorems can be proved simply when half-turns are used. In figure 4.3b, O is the common midpoint of the two segments. So, figure 4.3b. So you have a parallelogram, maybe? It's O, yeah? B, A, C, D. The half-turn about O takes AB into CD. AB into CD. AB into CD. Yeah, okay. Does it? AB. It takes AB into CD. See that?
Yeah.
Because A goes to C, right? And then B goes to D. Yeah? And the line goes to a line. Okay? So that shows that ABCD is a parallelogram. Oh. Whoa, wait a second. So this is a proof that if diagonals bisect, yeah, then we know then parallelogram, yeah? Ooh. Wait, is it obvious that it's parallel? Parallel lines go to parallel lines. Oh, we said that at the start, right?
Yeah.
Parallel lines go to parallel lines. Oh, that's a pretty slick proof, huh?
Yeah.
Yeah, remember those conditions. Diagonals bisect each other, like opposite angles are equal. opposite sides are equal and parallel. So that's the third one, right? That's pretty cool. The half turn takes showing that it's a parallelogram. Again in 4.3c, M and N are being the midpoint. Oh, 4.3c. Let me draw 4.3c for you. If only I could make use of the diagram I've already drawn. AB. C double prime. A double prime. Oh, there's nothing there. Something about N and M. I'm going to draw that in another color. Okay, let's see what it's asking us. So in this figure, M and N being the midpoints, okay? AB and AC, yeah. The sum of the half turns about these 2 points is the translation M double prime M or BC. Translation BC. Okay, let me draw in M and M double prime. M double prime is here. And this was like M prime. The translation about M double prime equals BC. Someone explain it to me? See it? So I guess there's two things to see. So there's the fact that it's agreed with what we were saying before, right? The sum of two half terms is a translation about twice the distance, yeah?
Mm-hmm.
So twice the distance is the reflection, that's why it's mm prime. And it's also BC because that's the midpoint, yeah? Okay, but let's look at the diagram. So M is reflected first, and then N, right? So A goes to A prime, and then goes to A double prime, yeah? And then B goes to B prime, and it goes to B double prime, yeah? And M goes to M double prime here. And it's still the midpoint of A double prime, B double prime, yeah? C prime. There's a lot of effort to draw, but I can't kind of see the point of doing.
Yeah.
So C goes to that one. It's a parallelogram of this, yeah?
Mm-hmm.
And then it goes to C double prime. Whoa, that's a long parallelogram.
Super.
Yeah, I don't quite understand what the point of it was, but yeah, I guess if we hadn't convinced ourselves that it was true, this was another way to do it, yeah?
Yeah.
A goes to, yep, then C does that, B does that. Yeah, so we checked A and B and C end up at the right places, yeah?
Yeah.
So let's check that also agrees with the conclusion. So A ends up along parallel to BC, yeah? Twice as far, yeah? Oh, this, I mean, the same length as BC. So that's a parallelogram, yeah?
Yeah.
Yep. C ends up here. Hmm. Yeah. B up there. Yeah, so C is probably the hardest one to check. Yeah. C C's double prime should stay in line with no, so C prime B prime should be parallel to C double prime B double prime, yeah?
Yeah.
Okay. And is C prime B prime parallel to BC? It is, right? Because that's just the parallelogram with the center M. Okay, so then this is on the same line, that's good. And it should have the same distance, right? As BC. Okay, so they all end up at the right places. So it's a translation by 2mm, or by BC in this case. Okay? Any questions? Hmm.